All right. Welcome to the webinar on exploring 2-micron laser plastic welding technology. Why are we having this webinar? Basically is to inform and educate on various aspects of the laser plastic welding field. So this first one is on 2-micron, and we will continue on from there. Want to focus on the specifics of clear to clear and provide expert advice so that engineers can begin to implement this into their applications. I want to clear up any ambiguities, help answer questions, and then obviously just to advance the general field of laser plastic welding and educate. So I am the host today. My name is Dax Hamilton. I've spent about 14 years or so in laser plastic welding, seen many different applications, both with through transmission welding and transparent polymer welding, 2-micron. My background is formally trained in CNC and manual machinist, both in tool and die, and also mechanical engineering. And I've got a lot of experience doing machine design from the ground up and so on and so forth. In-depth optics and laser experience, and I've had the privilege of working with most of the different suppliers in the laser plastic welding world over some years. Webinar host today is LPKF Laser and Electronics. And obviously, I think all of you have heard of LPKF, the best known global supplier of laser plastic welding equipment, and the world's first supplier to actually commercialize laser plastic welding technology. Basically, LPKF is a holistic provider of laser plastic welding expertise, which means we'll work with you from start to finish, not only just on selling equipment, but also the joint design and the material selection and so on and so forth. And we also are representing Optical Engines here today, and they're technically our sponsor. And as you can see here, Optical Engines has about 100+ years in combined experience, complex laser and fiber processing expertise, and they're the pioneer of the high-power air-cooled laser engines. The world's all-in-one laser engine diodes, power supply, driver, and safety all in one box. So a complete laser engine, completely integrated. So you just put this into your system or your automation line, and with optics and the scanner and so on and so forth, you can be welding. They're renowned experts in glass and fiber processing and beam manipulation technology, and the only supplier of a top hat shaped 2-micron laser and 1-micron fiber laser. And we'll get to that later in this presentation. So the agenda for today, we're going to be obviously giving introduction to laser plastic welding very briefly for those that aren't familiar with the technology. Key differences from through transmission laser welding. Typical applications you'll see, commonly welded materials, laser sources and optics, design criteria for 2-micron welding, something I call the 3 pillars, the nuances to 2-micron welding, and some special research. And then a summary, of course. All right, let's get right into this. Laser plastic welding. So it's obviously a very well-known bonding technology and enables joining of thermoplastics with high precision, cleanliness, and a minimized heat affected zone. Some of the advantages here, it's particulate free. You're not introducing any consumables like glue or with ultrasonic welding, you're vibrating 2 pieces together, so there's potential for particulate generation. It's very precise. You can get leak-tight seals. It's one of the highest bonding strengths of any of the plastics joining technologies, over 95% of the base strength of the material. Less weld flash is produced by laser plastic welding. No mechanical stress or vibration induced, and no damage to internal components, which leads to a reduced total cost of ownership. So real quickly, you're going to hear me use 2 terms today. One is through transmission laser welding, or TTLW, which is traditionally absorbing, transparent to absorbing. And you're also going to hear me use transparent polymer laser welding, which is what I'm going to be explaining here, TPLW for short. It's also been called 2-micron, clear to clear welding, clear joining. But in this presentation, I'm going to use these 2 terms respectively. So a standard through transmission laser welding on the left here, we use wavelengths in the range of 980 nanometers. In some cases, fiber lasers in the range of 1,000 nanometers, or 1064. There's different variants of the wavelength. And one of the joining partners needs to be IR transparent, and the other needs to be IR absorbing. Doesn't have to be clear or black to the eye, but they just need to either pass the IR energy or absorb the IR energy. And then for transparent polymer laser welding, we're using a wavelength in the range of 1,940 nanometers, or 2 micron. And both of the joining partners are transparent, IR transparent. They could be transparent to the eye, which is typically what it is, or in specific certain cases, there can be dyes or color in these parts. So like I mentioned, there's been many terms tossed around in the last 10 or so years. We're going to be calling it transparent polymer laser welding. So it's really important for bonding applications that require optically clear plastics without additives, most specifically in the medical device industry. Using transparent polymer laser welding, this eliminates the need for additives in the plastic that could affect any biocompatibility. Certain microfluidic and diagnostic devices rely on clear plastics, translucent or optically transparent plastics, to be able to look through and analyze the various fluids and whatnot inside the device. So while TPLW, transparent laser welding, polymer laser welding, has its nuances such as volumetric absorption, modified weld speeds, etc., it still fills a need where typical through transmission welding cannot. All right, so transparent polymer laser welding can be defined as a method of joining two IR transparent polymers by volumetric absorption of laser energy through the entire cross-section of the joining partners without the aid of absorbing additives or coatings. This is we kind of coined this as the official definition for transparent polymer laser welding. And you can see from these images here, the one on the left, you can see the material interaction with the laser, and it's volumetric from more or less from top to bottom. These are two pieces of plastic set on top of each other and welded in lap joint format. And you can also see another photograph of also some welding, the laser interaction with the plastic. Okay, why does this work? So if you look at this transmission spectra, this is an example for a PMMA, and you can see the different wavelengths across the bottom, and then the transmission percentages here on the left. So as you move up to roughly the 1,940 nanometers, you can see that the absorption is roughly, the transmission is around 70%, which means the absorption is about 30%. So what's happening is the optically clear plastics are absorbing roughly 30% of this laser energy. And so you're getting much more volumetric is the term, or kind of deeper penetration into the plastic. So wherever that beam is, you're getting interaction of the laser all the way through the potential pieces of plastic. Another key point here as to why this works is what I would call lens effect. And technically, it's not really the right term for it, but there are basically three possible modes of laser to material interaction: absorption, reflection, and transmission. So we're getting a kind of a culmination of all of those happening inside basically the pieces of plastic. And so where there's two pieces of plastic together, we're getting the majority of that, these activities in that with a weld joint area. And you can read there was a Journal of Laser Applications study that was done on this, and it definitely showed that the beam intensity was higher in the area where the two materials met due to lens effect. And this is caused by the refractive index difference between the two materials. All right, so TPLW explained. This is a graph kind of showing the steps of the laser material interaction. So it's two pieces of plastic stacked on top of each other in lap joint form. And we start to shine the laser beam, and basically the plastic starts to interact with the laser and heat up, and then slowly form this volumetric heat absorption down through the two pieces of plastic, with the result being this volumetric complete heating throughout the plastic. In context, through transmission laser welding, basically the laser is absorbed first by the lower piece that's IR absorbing. The heat and conduction starts at that layer, and then through heat transfer, basically transfers that heat up and then creates a melting and mixing due to thermal expansion in the middle of the joint there. Okay, I was supposed to take that picture out, but it's in there. I was kind of making fun of 2-micron laser plastic welding with advantages, where I had the AI create this, and it totally came up with some weird stuff, but thought I'd throw that in there. So advantages of through transparent polymer laser welding: no absorbing additives needed. So you don't need any sort of, I think it's green and blue, different IR absorbing chemicals in the plastics. You don't have to change the base polymer at all. So you can keep it in its natural state. You can do multi-layer welds. So you could stack up, I think we've done 12 or 13 layers of films. And since it's volumetric absorption, the laser energy will travel all the way down through these different layers. So it's a good option to have for multiple layers. Deeper welding penetration. So as I mentioned before, since typically the plastics absorb about 30% of the energy at 1940 nanometers, you can get the interaction, and again, it turns back to the volumetric absorption, where you can get this interaction all the way down through the plastics, therefore creating a deeper weld penetration. You can weld difficult to weld polymers. So this is kind of a traditional carryover from through transmission welding, where let's say we have a clear to a white, where the white material tends to refract quite a bit of the laser energy and can burn. 2-micron in some cases actually works better, even in a format of optically cleared or IR cleared to absorbing. It also has certain annealing properties, which I think we'll cover a little bit later, where it can more or less soften or relax the plastic from inherent stress and avoid any cracking or resultant afterward. All right, we're going to jump into applications. The pictures are all up here. I'm going to go through these kind of one by one as far as the applications, typical applications for 2-micron or transparent polymer laser welding. Tubing to fitting is a very common one. Actually, I don't have a picture of it here, but your typical stopcocks and lure fittings and different fittings like that in the medical industry for IV bags and fluid transfer. One of the most common applications I have seen for TPLW. Microfluidic devices, you can see one in the picture there, kind of in the middle. Different channels, so on and so forth. Very good for welding microfluidic films to slides and so on. Fluid and IV bags, very common. Sample trays and packaging. We've seen all these different applications come through over the years, and all work very well. All right, let's talk about some of the common materials, and I'm going to go through these really quick here. Polypropylene, polyethylene, TPU, thermoplastic polyurethane, PVC, cyclical and polymers, so CFCs and COPs, very common materials for 2-micron welding, polyamide, and PMMA, as well as PC. That's the last one here. Oh, and PET. So these are some of the most common materials we've seen over the years, and that all bond quite well with transparent polymer laser welding. I would say they're more or less in order from easiest to bond to some of the more difficult. So some of the PETs, PETG, difficult materials because the process window is pretty small and it tends to burn or bubble up quite quickly. All right, let's look at some of the design criterias. I'll jump into these because obviously the animation didn't work well. You don't need additives. The upper part thickness, so the first layer that the laser shines through, should be less than about 3 millimeters. This is kind of debated over the years, depending upon the laser power, the energy density of the laser. So depends on kind of the beam shaping. If it's truly Gaussian, we probably have to be a little less than 3 millimeters, maybe in the range of 1 to 2. But with the new top hat profiles that Optical Engines has in their lasers, we're able actually to get through a little bit thicker materials without burning that top layer. But still generally recommended that it's under 3 millimeters. And again, as I mentioned briefly before, the bottom part can be optically clear or opaque. Some of the nuances for 2-micron welding, I call them nuances. You can see them here in the picture. So the top left picture there is showing some of the volumetric absorption and somewhat thermal expansion there on the top. The picture in the next one over to the right, you can see a little bit of a kind of a radius in this T-joint. That's obviously from deformation. This is actually T-joint weld, and we're welding down from the top of this part. And then on the bottom piece, you can see it's kind of a half cutaway of a fitting, a medical device fitting, and you can see the thermal expansion happening in the channels. So we are welding from the outside in a radial format, and you can see this thermal expansion bubble starting to form on the inside of that part. There are ways around that. We'll get to that later in the presentation. And with transparent polymer laser welding, it's a bit slower of a process. That's not detrimental, but it's good to be aware of the fact that it's about 10 times slower than through transmission laser welding. So with that being said, we usually recommend to all of our customers that they look at through transmission laser welding first. And if that just absolutely can't fit their needs for their application, then we can look at transparent polymer laser welding. Jumping into the 3 pillars of transparent polymer laser welding. The first one, both the upper and the lower layers of the bonding partners are transparent. They can be optically transparent or IR transparent. More specifically, optically transparent, because some of the IR transparent materials, let's take, for example, nylon. Some of those in their natural state are somewhat milky or chalky colored or almost opaque. And so the 2 micron doesn't work very well with those specific materials. So try to say both the upper and the lower layers optically clear is probably the best case for this. We still need mechanical contact of some kind. So pillar number 2. We need basically those 2 pieces of plastic to be somewhat in contact with each other. And I'll get to that in the more detailed slide. And then we still need compatible materials. And we'll get to that. So diving into this a little bit more, transparent upper and lower layer. The biggest difference is that both of these materials transparent to the wavelengths of 1 micron and typically to the eye. No laser absorbing additives or coatings needed or can be used. And in some cases, like I said, translucent or even opaque materials can be welded, but they need to be very thin. So going back to when I mentioned nylon, being that it's in its natural state, it's somewhat milky, that just needs to be very, very thin of a layer for the top to be able to get the laser energy through without burning or adversely heating up and thermal expansion happening and melting. Okay. Actually, and then I wanted to include this white-to-white film. So I've done some testing with actually both materials being, again, very thin, but films can sometimes work as well, even though that they're not optically clear. So again, just to kind of get your thought process going here. Mechanical contact, like I mentioned, still needs to be held. With flat parts, it's easy to clamp with a glass plate, barring there's no features on the top of the part, etc. I mean, in some cases, you can do some machining of certain types of glass, quartz glass. You can grind borosilicate, so on. But it's very expensive and cumbersome and prone to chipping and cracking. So typically a glass plate's used for flat parts. But that doesn't limit us with TPLW to welding only flat parts. As you can see from the illustration below, this is just a cross section of a radial tube to fitting. Let's call it tube to fitting, for lack of better words. And we can weld those as they are interference fit. So pretty much any parts interference fit or clamping with glass plates is typical. Okay. And one thing that I do point out, the parts don't have to be tightly clamped together like we recommend for through transmission welding. And that is because of thermal expansion, because of volumetric absorption. So the laser, everywhere the laser is shining, basically it's heating up, thermally expanding, and in some cases can close those gaps. So it is something that we have going for us in 2 micron welding. Should point out too, if you just lay the 2 pieces of plastic flat and you shine the laser through it without clamping, they will weld in a lot of cases, but you'll see this raised bubble, this thermally expanded portion of your plastic. So just something to keep in mind. And material compatibility obviously is important. You couldn't weld a silicone to a PC. Just isn't going to work because of the molecular combinations. They are compatible. So chemical compatibility, thermal compatibility, so roughly a 50 degrees C overlap in melt temperatures. Then basically the optical properties, it needs to be suitable, like I discussed. Certain materials just aren't going to pass enough of that laser energy, okay? And then we obviously need rheological compatibility, melt viscosity, shear rate. Okay. All right, I'm going to jump into lasers for this specific 2 micron welding. Optical Engines has pretty much the only source that I've found on the market with a top hat beam profile, okay? So if you can look at the illustration here, traditional lasers, fiber lasers, single mode lasers are Gaussian in profile. through Optical Engine's special beam shaping technology inside the box, able to get a top hat profile, which makes it much, much easier, like I mentioned earlier, to not basically get any burns or, focusing that laser energy so precisely at one spot that it tends to burn before it's actually going to propagate that heat down into the parts. So a very important key feature. Air cooled. So this is the highest power laser on the market for 1940 nanometers, up to 250 watts. And it's air cooled. You don't need any chillers or any of those things. As me, my preference is I don't want water anywhere around my electronics, especially my laser. So this is a good reason for incorporating optical engines. They're quiet, 60 decibels or less for the cooling. And roughly 4 times higher efficiency over competitor systems. And I'm going to go into that here. The reason for that is it's a direct pump thulium doped architecture, whereas competitors have this cascade pumped. So this is the main reason to it being literally 4 times less in power consumption, much, much, much more efficient. And they are able to get up into this 250 watt range or even more, actually. It's compact, 4 rack unit, 4 19-inch rack units, it's a 19-inch rack mount, 4 units high. So it's about 6 or so inches high. And it's integrated again with the power supply, the driver, the software, the cooling. They have a feature called power lock, and it basically holds the laser power to a plus or minus 1% instability, which is very important. We've found in certain materials. So I think polycarbonate for sure is one of them that you have to keep within a certain, like just a few watts as your basically the process window. So this is very important to keep that right in that range. AMI beams included, and obviously there are thermal and pyrometer options that can attach to Optical Engine's lasers. And again, reach out if you have more questions on this. Happy to answer them. All right, so we're cruising through this pretty fast, a lot faster than I thought. I guess hopefully I'm not talking too fast. If I do, I apologize. So I wanted to cover a few, call it special research in transparent polymer laser welding, or maybe kind of some of the cutting edge stuff, and basically just kind of educate and let people know that hey, there's some options we have here, and we're working on testing. So the first that comes to mind here, working with alternate wavelengths. So not just 1940 nanometers, but looking at this transmission spectra and seeing that there was obviously valleys here where down in the let's say it's an approximately 1660 nanometers, the absorption is much higher than that 30%. In fact, up to roughly 85%. And then if you look up here at the over 2 micron, you can see that even more absorption can be had. So this is more or less just to kind of open your mind up just to look at, okay, there are different wavelengths, different absorption rates in these plastics. Doesn't just have to be 1940 nanometers, although that is kind of the more commercially available laser wavelength. And but I'm working personally with a certain laser supplier to work on testing these different wavelengths. And there's a few people out there that have tested different wavelengths as well. In certain cases, this could be beneficial because with that transmission rate being higher, then we can get a lot more energy into that plastic. But also it's going to, conversely, it's going to heat up a lot quicker, and we're going to have issues with thermal deformation and expansion and so on. So again, looking into this, it's new technology, potentially could work for thinner materials, films, so on and so forth, and get a better weld. And then there's different ways of clamping. So you don't just have to use a glass clamp. We've experimented with air pressure clamping, as you can see on the left here, called differential pressure clamping, where you can more or less pressurize a chamber to push 2 materials together without having to have glass or glass in contact with your parts. Another option is circumferential airflow. So it's a little bit hard to see here on the picture in the right, where you have kind of a thinner outer, maybe film, and then maybe a tubing substrate. And this ring here is radially drilled, and we'll have it's acting like a manifold with air pressure so that you can actually get air pressure circumferentially. So similar to the differential pressure clamping, but in a radial format. And again, this is just to kind of open your mind into what some of the possibilities are and get you thinking about different ways to clamp. So again, like I like to make sure that we're providing good education and kind of a start for people, customers that, have an application or are looking into applications to, to take this further. So the goal is just to freely educate. This has actually been a very interesting one. I apologize ahead of time that the graphics are a little bit small. Basically bringing the scan head. So hopefully you're all familiar with kind of how the beam gets delivered to the workpiece. It could either be a fixed optic in the case of radial welding, or it can be through a galvanometer scanner, which has two mirrors inside of it that are more or less CNC programmable to move and steer that beam around. There's other ways to get the beam to the part. Those are the two most common. In this case, I'm going to talk specifically about galvanometer scanner based beam delivery to the part. And by bringing that scan head or the F theta lens, basically the whole assembly, down to the point where we're using a highly convergent beam. Okay, so we're taking typically a beam that's probably, I don't know, 10, 15, 20 millimeters diameter. In some cases, may not be exactly that with the 1940 nanometer. And we're converging that down onto the workpiece so that effectively only the focal plane where we actually want to weld is in true focus within what's called the Rayleigh length. Okay, so we're kind of shortening that Rayleigh length down to the point where we're doing all of the effective work inside the weld joint. And the rest of the part, for example, is in the diffuse part of the beam or the defocused part of the beam. This is especially helpful when doing microfluidic parts. Let's say there's channels on the top and you have to weld a film to a substrate, and there's channels on the bottom and you need to weld again, or basically you don't want to affect those channels on the bottom by this thermal expansion properties, or you got to weld on the bottom as well. So kind of those two options. And we found that this works quite well to avoid any of the thermal expansion, volumetric absorption and expansion down through the part completely. Same can be held true for radial welding, as you can see with the bottom here. So again, focusing right at that weld joint. In this case, it's a conical or radial weld. Let's say it's a tubing to fitting application. We focus that, basically that beam right down at the center point of welding. Some cases it's difficult to do because of clamping, because of machine structures, but thinking with this in mind, this can avoid a lot of issues if it's needed to have, certain features or channels underneath or in the beam path of where the laser is going. So again, this will avoid any, like I said, thermal expansion of fluidic channels, tubing IDs, because it's staying in the defocus zone. And they can be somewhat minimized. It's not going to minimize all of it. Okay. All right, that covers the main part of the technical side of it. We'll go into a quick summary here. That didn't come through. Well, I apologize. Transparent polymer laser welding is a promising alternative to through transmission laser welding. I think that we all can agree on that. Has limitations, like I said, thermal effects, volumetric absorption, which also helps us in certain ways, deeper weld penetration, and it eliminates the need for any laser absorbing additives, and you can keep the plastic in its natural state. And thinking of the properties of the laser beam, including shape, size, angle of incidence, and intensity, this can have a significant impact on the quality of the weld. So again, one of the advantages to transparent polymer laser welding. So with that in mind, we are here to help. And like I said, we'll work with you completely from start to finish. Not only just on whether it's equipment or lasers, so on and so forth, but we'll help you with the material selection and guidance, joint design input, both technologies of welding through transmission welding and transparent polymer laser welding, prototype tooling and welding services, standalone and automated equipment, and also the vision inspection side of it, using machine vision to inspect laser welding, whether it's in situ as you're welding or after the fact as kind of a post-weld verification. And the whole goal is to navigate the tricky realm of laser plastic welding. So I hope this has been helpful. Apologize for any of the nuances with the presentation and the graphics, so on and so forth. But I hope, again, I hope it's been helpful, and thank you very much for taking your time out of the day to attend. And please reach out to myself if you have any questions, concerns, need input, and Hope you have a great rest of your day or evening, wherever you might be. Thank you and take care.